Hello everyone, welcome back to Stewart Technologies. In the last part of the series, we completed the mechanical design of the robot and tested each joint. This time we'll be upgrading the stepper drivers, adding sensors to the arm, and working on the control board courtesy of today's sponsor, PCBWay. PCBWay offers PCB manufacturing and assembly. You can get 10 two-layer boards for as low as $5, and new PCBWay members get a $5 coupon for their first order. That means you can get 10 PCBs for free on your first order. I know, right? They also offer a multitude of other services such as 3D printing, sheet metal fabrication, CNC machining, and injection molding. To learn more, you can visit PCBWay.com. You can find the link in the description below. Without further ado, let's get started.
In the last video, we saw that during operation the arm was very loud and vibrated a lot. This was because of the cheap stepper motor driver I was using. Not only was it an analog driver, but it also couldn't provide enough current to some of the motors in the arm. To solve this, I purchased 6 digital stepper motor drivers, 3 DM542Ts to run the lower 3 joints, and 3 DM320Ts to run the upper 3 joints. As we'll see later in the video, with these drivers, the motors not only run much smoother, but they're also a lot quieter.
As the robot arm is now, there's no accurate way to determine the position of the joints. The arm is currently operating through what we call open loop control, meaning there's no sensors to provide feedback on the positioning. If the arm were to skip steps, crash into itself, or a motor somehow fails, it would throw off the controller's estimate of its current position. To solve this, I'm going to be adding magnetic encoders to each of the joints to provide an accurate reading of the joint angle and limit switches to help with calibrating each joint. The encoder I decided to use is the AS5600. It's a 12-bit magnetic rotary position sensor that uses a diametrically polarized magnet to sense the absolute angular position. This sensor communicates through I2C but also has an analog output as well. I picked up a handful of these sensors for about $2 a piece on AliExpress. As you can see, by rotating a magnet on axis directly above the IC, we get an absolute angle output from the sensor between 0 and 360 degrees. The angle is absolute, meaning that if we power down the robot and move its joints, the sensor will still recognize the new angle on startup. Combining this sensor with a limit switch will allow the robot to calibrate itself if for some reason we lose track of the position in code. With the sensors in hand, I modified the CAD files for the robot to add in limit switches for each joint along with a mount for the magnetic encoders. For now, I have encoders on every joint except for J4 and J6 due to these joints having direct drives instead of gearing like the others. For these 2 joints, I'll need to add the encoders to the bottom of the stepper motors instead. This will take me a bit of time to work out, so I'll save that for later. Each joint except for J6 has a limit switch for calibration. I'll work on adding the limit switch for J6 later when I start working on the end effector. When all the sensors are integrated into the arm, we'll have 2 sensors per joint, making for a total of 12 sensors. Since 6 of them are I2C devices that need to be consistently pulled for data, the Arduino Mega will start to struggle to process all this information. To fix this, I decided to switch from the Arduino Mega to the much stronger TT4.1 board. The TT4.1 is a 32-bit microcontroller compared to the Mega, which is only 8-bit. It's extremely fast, has a ton of resources, faster clock speeds, and more interface options than the Mega. And best of all, it's also Arduino compatible. This will be more than powerful enough to handle anything this project can throw at it. To help organize all of the electronics, I decided to make a PCB. This board needs to handle a minimum of 6 I2C devices, 1 for each encoder, 6 limit switch inputs, 1 for each joint, 6 stepper motor control outputs, and 1 servo output for the end effector. I also added an extra input for another I2C device and another limit switch just because. Since the TT4.1 is a 3.3 volt microcontroller unlike the Arduino Mega, I needed some extra circuitry to interface it with the limit switches and stepper motor drivers. The stepper motor control outputs need to be at a 5 volt logic level, but the TT can only output a 3.3 volt signal. To help with this, I used the SN74HCT244N IC to turn the 3.3 volt signal from the TT into a 5 volt signal. For the limit switches, I've seen several issues online, mostly with CNC machines, where running the wires for the switches near stepper motor wires can induce noise into the signal, since the switches are typically driven at a much lower voltage than the steppers. To combat this, I'll also be running the limit switches at 24 volts and using the PC817 optocoupler to produce a 3.3 volt signal the TT can work with.
A board this large takes a lot of time and money to produce, so I'd like to thank this video sponsor PCBWay for providing me with the PCBs for this project. The boards look fantastic and the turnaround time was very fast. There were no defects on any of the boards I received, and the black solder mask looks amazing. So now that we have the control board, it's time to begin the assembly.
Hey there! If you're enjoying the content and you want to support me even more than you already are now, you can now do so through Patreon. Patreon members will receive exclusive behind-the-scenes posts about future projects, early access to project files, and early access to videos up to a couple hours early. The link to my Patreon will be in the description below.
Now that the board is fully assembled, we need to test it. First thing I want to do is make sure all of the voltages are correct. I'd rather catch any issues now so I don't fry any of the components accidentally. Once that's all verified, we can test the circuitry for the sensors with this simple Arduino sketch that initializes the sensors and prints out their current state. As you can see, everything seems to be in good working order. We get the angle output from the encoder and a high or low value from the limit switch. With the board working, now all that's left is to clean up the electronics a bit and connect everything together. I moved the power supply and power distribution blocks over to a larger piece of plywood so I'd have more space for the new components. Since now I need to fit 6 stepper motor drivers, the control board, which is about 7 by 6 inches big, and a new enclosure for the emergency stop button. In the future, I'm considering moving all of this into a separate enclosure with connector ports on the outside for the robot to plug into. That way I can also add in cooling for the stepper motor drivers. But for now, this will do. Here we have the finished control layout. We have the motor wires going to all 6 joints. We have the encoder wires coming in for J5, J3, J2, and J1. As I mentioned before, J6 and J5, I have to work on the encoders for those later. And here we have the end stop wires coming in for J1, 2, 3, 4, and 5. We'll do J6 later. And we have all the stepper motor inputs for all 6 joints as well. I had to remove the 5-volt voltage regulator, the 7805, because it was overheating. I was drawing too much current, and because I'm powering it at 24 volt, that means there's a lot of heat being dissipated. And rather than adding like a fan right now or a huge heat sink for it, I just removed it and I'm using an external 5-volt power supply instead. We have our emergency stop button here, power distribution, everything's good. Coming over to the robot, we have, you may notice that all the wires are in this nice braided sleeving here. And this is actually an issue for reasons I'll get into in a bit. But we have the cables coming out from this joint hub and this joint hub, and they're wrapping around here, going into the control board, and we have the same thing on the other side as well.
Here, let me click that E-stop real quick. So as you can see here, all the joints on this side as well, coming from J6 down. And everything has enough slack where it has complete range of motion, and it's cool looking. Everything's nice. So the first test we're going to run is just a basic controls test where we're testing all of the encoders and the end stops for the robot. So if we look over here to the Arduino side of things, we have this basic control board test. And as I mentioned earlier, we're just setting up all of the encoders, and then we're just printing out their state to the serial monitor. So let's go ahead and plug up the TNT and upload the sketch. So as you can see, it's going through setting up each encoder, and once it's finished, we get a list of values printed out to the serial monitor. So that first value, where it says 1.1 right now, if I rotate it, that's the angle value for J1, and everything's working there. The next value after that currently says 348.8 is the angle value for J2. So if I lift up this limb and move it, you can see the value changes. The next value that says 125.2 right now on the screen is J3. So if I move this, that value changes. And then the next value that says 9.7 is J5. So that changes. And now looking to the right of that, where it says 1 right now, that's the end stop value for J1. So the end stops are wired in a normally closed fashion, meaning that when the switch isn't pressed, the switch contacts are closed, so it'll be a logical high. That's why you see the 1 there right now. So if I were to turn J1 all the way, you can hear the click, and you can see it's switching from 0 and 1. So it's pressed, not pressed. Same thing for J2. It says 0 right now because the end stop is in the closed position when it's lying back like this. But if I lift it up, it switches to 1, put it back down, goes to 0. Same for J3. It says 0 right now, lift it up, it goes to 1, put it down, 0. J4's end stop is also in the bottom right over here. So if I rotate it this way, it says 1 right now, then it went to 0. And the next value is for J5. So if I turn it, 0, 1, 0, 1. There are 2 zeros in there that didn't change, and those are actually just 1 0 that didn't change, and that's just for J6 at the very end, because it's not installed yet. That'll be done later. But now that we know all of the joints are working properly with the encoders and the end stops, we can start testing out the positioning of the joints, starting with J1. So the sketch I wrote, the code is a mess. It's not going to be used for the final design. It was just something I threw together to test each joint. I go through and I set up the stepper motors and the encoders, and just the same as in the other code. And I set my max speed, acceleration, things like that. And I go ahead and home the joint with a function that I made. And now this function just moves it to a very extreme value until it runs into the end stop. And once it runs into it, it takes the encoder value and it uses that to offset to sort of calibrate the angles for each joint. So if we go ahead and upload this and also release the end stop or the emergency stop. So now it says homing J1. So give it a second and now it should start turning. So I'm turning at about 100 revolutions per second, and the micro stepping for all of the motors are half stepping, so 400 steps per revolution. I'm going to play around with that later on. I know a lot of people have been asking me about it, but you can tell already it's quite quiet compared to before with just half stepping. So I'm sure we can get the motion even smoother with higher micro stepping values. So now looking at the serial monitor, it says we're at 350 degrees with 0 error and 0 steps to move. So let's say we want to move it to the midpoint, about 180 degrees. I type 180 into the serial monitor and I hit enter. Then J1 begins to move. And you can see that the error is negative because it has to move in the negative direction. Or excuse me, the positive direction, excuse me. And then it says steps to move. And there. Now we're at 180 degrees. You probably can't see it on camera, but the front lines up with a little mark that I added in CAD. to let me know that this is exactly the midpoint. Let's try one more value before we move on to a different joint. So let's say I want to move it to about some arbitrary numbers. So like, I don't know, 70 degrees. So I type 70, hit enter, the joint starts to move. All right, so as you can see, the joint moves to 70 degrees. So before we move on to doing joint 2, let's just put J1 back to 180 degrees to give you a good view of J2. And then we just upload the code for J2. So some of the angles might be off by a few degrees compared to what I have in CAD with what I want, like 180 and 90 to line up to on the robot. I can fix that later, but for testing, it really doesn't matter. As long as I know that the value I'm getting from the encoder is matching what I'm telling the robot to move to, I can sort of shift values and move things around later. So let's go ahead and upload the code for J2 to the Teensy. Now, the arm might not move because it's already touching the end stop. So when it says homing, yeah, it doesn't move, but it'll move up after homing. Then it'll move down again. So the reason that's happening, I just have it moved to a ridiculously extreme value. And when the end stop is clicked, it gets that offset value, and then I have it moving 10 degrees here in code. Now, this code is wrong, like the math I was doing here was wrong and some other things like that. So it's not actually moving 10 degrees, or at least not according to the value of the encoder. Like I said, they don't line up just yet. And then I have it up here going to 10 degrees. So it corrects itself to what the encoder says rather than what my math says or is telling me or whatnot. Now we're lined up with what the encoder says, 10 degrees. So let's say we move to about 95. And as you can see, J2 starts to rise, just like J1 did until it gets to the position. And there, we're at 95. And I know you probably saw as it was moving up, it kind of tilted forward a bit and then started moving again. The belts are slipping for that joint. And I think it's because of the cheap hardware I'm using for the gears. The hubs that I'm using to attach them to the shaft, the set screw is very weak, and you can't really screw it in without stripping it too much, and it doesn't really get a good grip to lock it in place. So I'll be replacing those later to make sure everything's moving smoothly as it should be. But as you can see, the positioning for J2 is working, so let's try another value like 120. It moves forward, gets to 120, then stops. So that's working fine. So now let's try doing J3. So I'm going to move it back to about 90 degrees, and then we're going to upload the sketch for J3. Now we may run into a problem here because I'm enabling all of the stepper motors as I'm testing them in each sketch. And if it happens, I'll tell you in a second. But J3 should home, and again, it's already clicking the value, so yep, there you go. It moves up. Right now it's at 330 degrees. So let's say I want to move to 270. And I hit enter, and it starts moving. And see, this is what I was talking about. If you look here in the serial monitor, the output stopped. It stopped at about 282 degrees, and the code kind of just freezes. This goes back to the issue I was talking about with the braided cabling and running everything together in one sleeve. All of the I2C lines are running at 3.3 volts so they can communicate properly with the Teensy. That's not a problem normally if it weren't for the fact that all the stepper motors and end stops are running at 24 volts and there's noise being generated from the control signals being sent from the drivers, and as well as just from being near the stepper motors. So what's likely happening is the noise is too much for the I2C interface on the Teensy, and the data is getting corrupted, garbled, and it sits here waiting for data from the encoders that just never arrives, basically. Or at least it just can't get back in sync and receive the data as it should be. Now in code, you can fix it so that if you don't receive, your data within a certain time limit, you restart and whatnot, which would be fine, but there's no telling how many times it would start and stop due to noise and interference. Luckily, I thought about this already, but I was just a bit too lazy to implement it now because I wanted to get the video out. But I bought some of this wire right here. This is shielded 4-conductor wire, 22 gauge, and I'm going to be running that wire for all of the encoders in the robot. And instead of bundling it together with the stepper motor wires and the limit switch wires, I'll just be running it alongside it on the outside. So hopefully that will be enough to mitigate any noise you may have in the system for those lines. And I'm also not using any input pull-ups for the encoders right now for the I2C. I could add input pull-up resistors or maybe use the Teensy's built-in resistors depending on the values, and that might help as well. And right now, as you can see, there's just a rat's nest of wires, which is not great for noise. You have stepper motor wires running on top of and around the encoder wires. Plus the lengths of the wires are a bit too long right now, longer than they need to be. So what I'm thinking about doing in the future, I know I mentioned it before, but developing an enclosure with ports on it. So all of the wires on the robot can be terminated with connectors and I can just sort of plug them in. And that way inside the enclosure, I can run things with shielding or further apart as needed to mitigate noise even more. So I can't show you any more of joint 3, and I believe joint 5 has the same issue just because the encoders for both of those are further away than J2 and J1. But we're gonna try, so you can see J5. Now let's go ahead and upload a test sketch for J5. So if it works, you should see it home itself and then back off to a certain angle, and then I should be able to tell it to move to different angles. So there, it homed. Yeah, and see, if you look at the code here, it stops right at 19 degrees and it doesn't correct for the air at all, which is no good. I think it's just that signal issue with I2C. That's all the testing we can do for now until that gets fixed. But as you can see, all the sensors are working as they should be, minus the noise issue. All the positioning is working great for the arm. And when I didn't have everything bundled up together in that one braided cable bundle, everything was working. I was able to do J5 and I was able to do J3 perfectly without any issues. So those problems need to be fixed before we can move forward, but that'll have to wait until a later date. In the next video, I have a huge list of stuff to do. We'll be fixing the things we just discussed, working more on the control software, and figuring out what we're going to do with the end effector. If you have any questions or comments about the project so far, feel free to drop them in the comments section below. If you like this video, share it with a friend, and make sure to like, subscribe, and click the bell to receive notifications when the next video drops. Thanks for watching.